Okay, so for number one here, we have the two similar figures here, kind of a weird hexagon, six-sided figures. We see we're given these two angles. Oops, get back here. Oops, it's not showing up. Let me try to resend it. Okay, well, let me, so that was actually going to be one of my things I wanted to mention tonight anyway. Technically, it's actually 421, but if you were at 420, it would round up. If you do not have at least 420 total points, if you look in Blackboard right now, you are in danger of not having enough to get a C to pass the course. So make sure you're looking that up, and if you are below that level, contact me and we'll see what you can do to earn more points back. The other thing, as I had mentioned before, if you had to complete any quizzes late, if you had to have any quizzes reopened and completed after the due date, make sure you go back and compare My Math Lab to Blackboard. And make sure that they got transferred to Blackboard, because like I said, it is really difficult to find late quizzes and transfer them over. I literally have to open up both grade books and look at them side by side. And then My Math Lab grade book does not fit on one page, so it's really tough to compare them and see. So if you've done any quizzes, and it's a good idea just to compare anyway, make sure your quiz grades in My Math Lab and your quiz grades in Blackboard match up. Some differences might be just accounted for by a late penalty, but other than that, make sure they're there. Okay. Everything's looking good up on the screen there now, right? Okay. So I'll put these back up here so you guys have a chance to work on them. Find X, Y, and Z in problem number one here, and then find Y and Z, or X and Y in problem number two. I'll give you, like I said, about a minute. Okay, so for number one here, we can see these angles here are marked that they're together. So that just tells us that these two shapes are in the same orientation. So the 28-foot side in this figure corresponds to what side in this figure over here? The 14. In fact, there's the side where we know both lengths. So we've got 28 to 14. Now let's just go in order here. We'll find X first. Is X going to go on top or bottom in my proportion? It'll go on bottom because it's from the same figure as the 14. What's going to go above it? 4 is the corresponding side from the other figure. Perfect. So we cross multiply and divide. 4 times 14 or divided by 28 gives us X is 2. So now we're going to still go back to that 28 and 14. 28 to 14. Now we're going to find Y. Is Y going to go on top or bottom? It goes on bottom because it is also from the same figure as the 14. What goes above it? 14 is the corresponding side in the other figure. So now for this, we're going to cross multiply and divide again. 14 times 14 divided by 28 is going to give us that Y equals 7 feet. So we've got one more side to find there, Z. We're going to keep the 28 over 14. Z going to go on top or bottom? Top, because it's from the same figure as the 28. And the corresponding side from the other figure is the 20 feet. So now we will cross multiply and divide there. It'll be 28 times 20 divided by 14. Z is 40 feet. Any questions on that one? It's relatively easy to match them up when they're set in the same orientation like these two were. So in number 2, the orientation does not match up. Each of them has two sides where we know the length of. I need to find at least one side where I know the length in both figures. Can you tell me what those sides are? Okay, the 9 and the 12. You can see the 9 is with the angle with 2 hashes and the unmarked angle. The 12 is also between the angle with 2 hashes and the unmarked angle. So those are the corresponding sides, and we know both lengths. So 9 and 12 correspond. Going in order again, we're going to go with x first. Does x go on top or bottom? Top, because it is from the same figure as the 9. What's its corresponding side from the other figure? The 24. So that'll go on bottom. Now we can cross multiply and divide. 9 times 24 divided by 12 will give us 18. X is 18, and this is inches now that we're working with here. We're still going to do the 9 to 12 again. We're trying to find y, top or bottom. It's going to go on bottom because it's from the same figure as the 24. What's the corresponding side from the other figure? The 12 goes on top. So now we'll cross multiply and divide. 12 times 12 divided by 9 is 16. Good. So y is 16 inches. Any questions on those? Okay. So where we left off, I had asked you to do some graphing for me on a worksheet, and we had some of my math lab homework. But we had graphed using tables. We had taken an equation like y equals negative 2x plus 5 to the equation, and we took a table where we picked values of x, and we used the equation then to calculate the value that y had to be given those values of x. Then we plotted points on the graph. For example, if I pick negative 2 for x, well then y has to be negative 2x plus 5. Well, we put in where the x is, we put in the negative 2. So negative 2 times negative 2 plus 5. That calculates out negative 2 times negative 2 is positive 4 plus 5 is 9. So that gives us the point negative 2, positive 9. So negative 2, positive 9 is right there. Somebody give me another value to try for x. 0 is a good one. I always like to use 0 because it's usually relatively simple to find. So negative 2x becomes negative 2 times 0 plus 5. Negative 2 times 0 is 0 plus 5 is 5, giving us the point 0, 5. So that gives us a point right there. Somebody give me another point to try for x. Negative 1, okay. So now we have negative 1 goes in for x. Negative 2 times negative 1 plus 5. Negative 2 times negative 1 is positive 2 plus 5 is 7. So when x is negative 1, y is 7. It's right there. I'm going to pick one more. I'm going to use a positive 1. Negative 2 times positive 1 plus 5. Well, negative 2 times positive 1 is negative 2 plus 5 is 3. So when x is positive 1, y is positive 3. Well, we've got 4 points in a row in a line. That's relatively good assurance that that's going to form a line on our graph. And there's our line on the graph. How many of you, show of hands, got time to do that graphing worksheet that I posted on Blackboard? Just a couple of us? Okay. Well then, a few. Let's take a look quick right now at those equations. Number 1, what was the equation for number 1? Anybody have it with them? So 3x minus 2. Perfect. What's the equation for number 2? Six minus x. Number 3. Okay, number 4. Number 5. Number 6. Number 7. Number 8. That's going to be a fun one. Number 9. And finally, number 10. Okay. So I'm going to just sketch the graph of each of these quick so you can see them. Number 1 here, y equals 3 minus 2x. It looks something like that. It's going to be a line. Pretend that looks straight. Number 2 is also a line. Looks something like that. 3 is not a line. It looks something like that. It's called a parabola. 4 looks something like that. Now you'll notice a difference here on 4, by the way. So far, all of these I put arrowheads on both ends of the lines and on both ends of this curve, the parabola. Over here, I put an arrowhead on this end, but not on this end. Can anybody think of why I would not put an arrow there? Well, because that graph cannot go that direction any further. That's negative, x equals negative 6 here. If x was negative 7, what's negative 7 plus 6? Negative 7 plus 6 is negative 1. What's the square root of negative 1? Your calculator would give you an error if you tried to do that. So we cannot take the square root of negative 1. Because of that, we can't take the square root of anything negative. So because of that, x cannot take on any values less than negative 6. If this were a college algebra class, a formal algebra class, we would talk about domain restrictions. We cannot do, the domain here is restricted, the x has to be greater than or equal to 6. Number 5, y equals 3 plus 3x is going to be a line looking something like that. Number 6, y equals 2 to the power of x. Looks like that. That's actually called an exponential curve. Now, again, this has some limits. You'll notice this never goes below here, no matter how small x gets. X could be negative 200. It's still going to be a little bit more than 0. It'll never equal 0 or be smaller than 0. That's called an asymptote. Again, that's not something we're going to focus on in here, but if you were to go on to a college algebra class, you would talk a lot about asymptotes. They're another limiting form of the graph. Number 7, x to the third minus 1. Looks something like that. Number 8, I had said was going to be fun. Depending on your point of view, that might be viewed as a little bit sarcastic. It actually looks like that. It's tough because a lot of people want to try to connect it between here But you can't, because if x is 0, what's 8 divided by 0? Well, your calculator gives you an error again. Can't divide by 0. This is another case where there's an asymptote here. X can never equal 0. This graph can never cross x equals 0. So because of that, it ends up being two separate pieces like that. Number 9, 4x squared minus 8. Looks something like this. It's actually a parabola, just like number 3, only it's a lot narrower. And finally, number 10, 3/4 x minus 4. It's going to look something like that. Did anybody have all those look the same as what you got on your paper, except for maybe number 8? A couple of you real close. Okay. Anybody like totally baffled as to how I got any of those shapes? Okay. Now, the fact that I was able just to, from the equations, I was able to just very quickly sketch out the shapes might be an indicator that there's a shortcut to graphing these. And there is a shortcut to graphing them. And the first part of that shortcut is knowing what shape they make on the graph. Now, for our purposes here, we're going to focus on lines. So we're going to look here at the 4 equations, the 4 graphs that form straight lines. And what I want you to do is look at those equations that made lines, and then look at the equations that did not make lines. And I want you to tell me what's different about them. More specifically, the ones that don't make lines, what do they have that the other ones don't have? Exponents is the big one. And to be specific, it's exponents on a variable. So that describes what's happening with this one here, because we had the x squared. This one here, because it's x to the third. That describes this one, because it's x squared. In fact, it even describes this one here, because technically you could view that instead of the square root of x plus 6, you could view it as y squared equals x plus 6. So that describes those. What would describe what's going on with number 6? It still has to do with exponents, but instead of an exponent being on the variable, in number 6 there, y equals 2 to the power of x, the variable is the power of an exponent. It's not x to the power of 2 or x to the power of 3, it's 2 to the power of x. Then the final thing is number 8 here. What's going on there? Be brave. 8 over x is 8 divided by x, so that would be dividing by a variable. These things here that we just listed off are what I call the 3 don'ts of linear equations. Because equations that make straight lines on the graph, I shouldn't say straight lines, that's redundant. Equations that make lines on the graph don't have those 3 things. If there's an exponent on a variable, not going to be a line on the graph. If the variable is the power in an exponent, it's not going to be a line on the graph. Or if we're dividing by a variable, or the variable's in the denominator of a fraction, same thing. It's not going to make a line on the graph. So let's look at some equations. Is that going to form a line on the graph? What about that third power there? Does that make a problem? No, it doesn't. That's just 2 to the third power. This is just y equals 7x plus 8. So yes, that is a line. How about this one? Y equals 5x minus 3 plus 6x. Are there any powers on the variables? Nope. Are the variables in the powers? Nope. Are we dividing by a variable? No, that is a line. Again, that could be reduced to y equals 11x minus 3. How about that one? What's wrong with that one? X squared, that cannot be a line. Good. How about this one? Dividing by the variable, that cannot be a line. How about this one? Why not? The variable is in the power of an exponent, so no, that cannot be a line. How about that one? Careful though, we're not dividing by the variable. It's x divided by 7. So yes, that will still be a line. Yeah, the variable is divided by a number, not a number divided by the variable. You can't divide by the variable. So basically, we've got it down to what we can look at an equation and know what makes a line and what doesn't. So we're going to spend time tonight focusing on graphing those lines. Once we know that the equation is going to be a line, what's it going to look like? So I'm going to start out here graphing some lines. And I'm going to start with the simplest possible linear equation I can think of. That's y equals x. There's no powers. The variable is not in a power. Definitely not dividing by a variable. I'm going to make a little table here. And I'm going to pick some values. If x is negative 3, what's y going to be? Negative 3, good. If y equals x, if x is negative 3, y is negative 3. So negative 3, right there. If x were 0, y would be 0. 0, 0 is right there. If x were 2, what would y be? 2. So x is 2, y is 2. Obviously, that forms a line. 2 things I'm going to point out about the line. It goes through the origin, the center of the graph, and it goes corner to corner across the graph at a 45-degree angle. Now, we talked about building equations before, to make them more complex when we just did one variable equations. And things we did were adding to the equation, subtracting, multiplying, dividing. We could do powers and roots, but that would make it not a line anymore. So to deal with lines, we can only do adding, subtracting, multiplying, and dividing. So let's look at y equals 2x. See what happens there. Well, if x is negative 3, what's y now? Negative 6. Negative 3, negative 6 is right there. If x is 0, y is 0. 2 times 0 is 0. That's still there. How about if x is 2? Y is 4. 2 times 2 is 4. So x is 2, y is 4. We still get a line across the graph. All that has changed is that line is now steeper. So multiplying by 2 but multiplying by a large number makes it steeper. So if multiplying makes it steeper, how do you think I would make it shallower like this? Divide, right? Like y equals x divided by 3. Now, rather than doing x divided by 3, what we would usually do is we know that 1/3 times x is the same as x divided by 3. So now let's take a look. If x is -3, what's y have to be? -1, perfect. So -3, -1. If x is 0, what's y have to be? 0. If x is +3, what's y have to be? +1. So we get a line still. It's still going through that origin. It's just shallower. It's not as steep as the others. So all of these lines go through the center of the graph at the origin. If I multiply by a number, it makes it steeper. If I divide by a number or multiply by a fraction, it makes it shallower. So let's look at adding. Let's do y equals x plus 2. So now, let's say x is -3. What's y have to be? -1. So -3, -1 is right there. Well, that's on that green line. Let's see if we stay on. Let's say x is 0. What's y have to be? 0 plus 2 is 2. So 0, 2. It's not going to be on that same spot, is it? If x is +2, y would be 4. So +2, 4 is right there. So there's two things we'll notice here. It doesn't go through the center anymore. In fact, it did what? It moved up 2 spots, didn't it? But also we might notice that it's parallel to that first one we drew, the black line, the y equals x. So it's back to going across the graph at that same angle. It just moved up 2 from there. Well, let's try. What do you think would happen if we did y equals x minus 3? Well, now if x were -3, what would y be? -6. So -3, -6 is down here. How about if x is 0? 0 minus 3 is -3, so right there. If x is 2, -1, so 2, -1 is right in there. We see, first of all, it's still parallel to that original black line. You see, it's still parallel to that black line that we started with. It is now just moved down 3 spots from the center of the graph. Hence the -3. So adding or subtracting just moves that original line up or down. The multiplying or dividing changed the angle across the graph, made it steeper or shallower. All of these lines, however, as we move from left to right, are going up. How do you think we'd make it go down going left to right? We might have y equals -2 times x, multiplying by a negative. Now, kind of ran out of space here. Let's say x is -3. What's y have to be? Well, -2 times -3 is +6. That's going to be somewhere in here. If x is 0, what would y be? Well, -2 times 0 is 0, right there. And if x is 2, y would be -4. So 2, -4. So you can see multiplying by a negative does make that line go the other, angle the other direction across our graph. So there's only 2 things that can happen to these equations. So let's take a look at something like this. Y equals 2x minus 3. All graphs start at the origin. This number right here that is added or subtracted to the variable moves us up or down from the origin. Since that's a -3, we go down 1, 2, 3. So this line starts there at -3. That's referred to as the y-intercept. The long term, it used to be called the y-axis intercept. They just have shortened it. This is, remember, the y-axis here. That's where the line crosses the y-axis. It intercepts the y-axis. The 2 tells us that we're going steeper than normal. Remember, the regular line just went 45-degree angle. The 2 says it's going steeper. That number that multiplies the x is called the slope. To understand these graphs a little better, make them easier to graph, we're going to have to talk a little bit about the slope. Slope is always a fraction. The numerator of that fraction is the rise, and the denominator is the run. Well, you might look at this and say, well, 2 isn't a fraction, but any number really is a fraction. I just make it 2 over 1, like that. So rise means that from a starting point, and that starting point was what we found right here, that y-intercept. From a starting point, we go up or down if it's negative. That many units. So we rise 2. The run, then the bottom number, tells us to go over. We go over left to right, the positive direction on the number line. So since that's just a 1, we're going to run 1. There's the second point on our line. Our line goes through those 2 points. So let's look at some examples here before we go to break. We might have y equals 2/3 x plus 2. So on the graph here, this line is going to start at what? The +2. That's the number that's added or subtracted. That is the first point on my graph. Now the 2/3 is a fraction. That's our slope. Which number is the rise? The 2. The numerator is the rise. So from this starting point here, we go up 2. And then the 3 tells us to go over 1, 2, 3. There is the second point of our line. Our line goes through those 2 points. Now, if I wanted to, I could go up 1, 2, over 1, 2, 3 again. Notice that's another point on the line. And oftentimes when I'm graphing them on paper, I'll do that. Just with only 2 points, it's awfully hard to get that lined up perfectly straight enough to make that line look nice. What if we have y equals -3/4 x plus 1? Where does this one start? +1 right there from the +1. Now, -3/4, the negative always goes with the rise. The run is always positive. So -3/4, it's -3, which means from this point we go down 3. Perfect. Then from there we run 1, 2, 3, 4. The run is always positive. So our line goes through those 2 points. Now I said the run is always positive. I should give you a little clarification that -3/4. That can either be thought of as a -3 over a +4 or a +3 over a -4. Either one gives me a negative overall number. I cannot have -3 over -4 because a negative divided by a negative would be a positive. And that's the mistake most people make, is they want to make both of them negative when the slope is negative. You can't. Only one or the other. That's why I always say that you make the rise negative and the run is always positive. That's how we had the down 3 over 4. But you could have, if you wanted to, kept the rise positive going up 1, 2, 3, and then you make the run negative, so you go back 1, 2, 3, 4, like that. Notice that's still on the same line, it's just a different point on that line. What do each of these lines represent? Well, that gray line there, of course, goes with this top equation. It represents all of the solutions, all of the pairs of numbers that make that equation true. If I pick out a point right here, let's say I trace that down, that's x equals 1. I trace that over this way, that gives me y equals 2 2/3. If I put those into the equations for x, put 1 in for x and 2 2/3 in for y, it's going to make that equation true. So every point on that line, if I take its x value and its y value and put them in this equation, it will make that equation true. So that line represents all of the solutions to that equation. Let's graph some more examples here. So here, where do I start graphing this one? Yeah, it's in a different order, but it's still the number, the -2 is multiplying x. So that's got to be the slope. So it's the 5 out here. It's a positive 5. So it's plus 5. That's the number being added or subtracted. That's the y-intercept. So we start right there. Now this is a -2 times x. We make it a -2 over 1. So from that starting point, we will go down 2. That's the -2. And then over 1. That's the one on bottom here. And so our line goes through those 2 points. Any questions? Okay, I'm going to have you guys graph a few here. Y equals -3 minus 2/3 x. Y equals 3 minus, or 3 plus 4x. Y equals -2/3 x minus 3. Let's just have you graph those 3 for now. Okay, so number 1, where would we start there? Start at the -3, perfect. So that's our first point. From there, what do we do? Well, it's -2/3 x, right? So the negative will go with the 2, and from this point, that means we go down 2, and the 3 in the denominator means we go over 3. So there's our second point on the line. The line's going to look something like that. The second one, where are we going to start? +3 right there. Now the slope of 4, we make it a 4/1. Then what? Up 4/1. There's our second point. So obviously that's a pretty steep line. And then finally, the last one. Where do we start? -3, and from there we go down 2/3. That's the same line as the one in the blue. What's different about this fourth equation I'm going to put up here? What's different about that one? Well, it's not just y equals anymore. All these were y equals, weren't they? This is y plus 2 equals. Y is not alone. In order for this graphing to work, it has to be, the y has to be alone. It has to be y equals and everything else on the other side. Well, perfect. Yeah, y has had 2 added to it. So to get it alone, we would subtract 2. When we add or subtract, if you think of whole numbers, like 378 minus 5, I only had to subtract that 5 from one digit. Right? I subtracted it from the ones digit. The digit that had the same name as it. So when I add or subtract, I only have to add or subtract from one digit on each side of the equation. So I subtracted 2 over here to make that 2 go away. That leaves me with just x. Now, to keep this scale balanced, I do have to subtract 2 on the other side. What digit am I going to subtract 2 from? The 3. So the 3/4 x doesn't change. 3 minus 2 is 1, +1. So that graph would start out at +1, and from there it would go up 3/4. The over is always left to right. Well, building on that, we might see something like this. 3y equals 2x minus 6. What's going on here? Yeah, y has been multiplied by 3. So to get it by itself, I have to divide by 3. Canceling that out gives us y. When we multiply or divide an equation, if you think about 243 times 2, that 2 multiplies the 3, but it also multiplies the 4 and the other 2. When we multiply or divide, we have to do it to every digit. So here when we multiply, or we divided 3y as a single digit. We divided to cancel out the 3. On the other side, we have to divide each of those digits by 3. 2x divided by 3 is not as difficult as it looks. I just do 2 over 3x. Negative 6 divided by 3 would make negative 2. So to graph this, we start at negative 2 and go 2 up, 3 over. There's our line through those points. I just realized I went way past the start of break time here. Sorry about that. It is 4:28. Let's take a break and come back at 4:38. So the next step is we would have more than one thing that needs to be done before we can graph it. We might have something like this. 2y minus 5 equals 3x minus 1. So we need to get y by itself. So that's right here. We need to get y right here by itself. Just like when we were solving equations before, we look at how this was built and we take it apart. If y was a number, what's been done to build this is it's been multiplied by 2, and then 5 has been subtracted from it. But remember, when we take it apart, we take off the last piece that was put on first, right? So to start taking this apart, what's the first thing we would do? Careful. The multiplying by 2 is the first thing done, then the 5 was subtracted. So to take it apart, we'll add 5. We go backwards. Now remember, when we add or subtract, we only have to do it to one piece on each side. So we add 5 there, it gets rid of the negative 5. On the other side, where do we add 5? To the negative 1. So we still got 3x. Negative 1 plus 5 is positive 4. Now we have to get rid of the 2 by dividing by 2. Makes that 2 go away. But remember, when we divide or multiply, we have to do it to every digit on each side. So the 3x divided by 2 is 3 over 2x. We also have to do 4 divided by 2, which is positive 2. So to graph it, we would start out at positive 2, and from there we would go up 3 over 2. And that's where our line goes. Of course, the final stage of that, oops, get out of here, will be an equation that looks like this. 2x plus 5y equals 10. To graph that, again, we still need to get y by itself. So y here has to be isolated. If we look at how this was put together, y was multiplied by the 5, and then the 2x was added to it as a unit. So to take it apart, I go backwards, I subtract the 2x all as one piece. That's going to go away. That'll leave me with 5y. We have to subtract 2x from the other side, but there's really no place to subtract it from. There's nothing with the same name. So 10 minus 2x is just 10 minus 2x. And then we have to divide by 5 to get rid of the 5. Leaves us with y. Dividing by 5 over here. What's 10 divided by 5? 2, but then we also have to do the negative 2x divided by 5, which is negative 2/5 or negative 2 over 5x. So to graph that, we would start at the 2, right? And from there, we would go negative 2/5. The rise is the negative 2, so we would go down 2, and then we would run 5 over 1, 2, 3, 4, 5. There's our graph. What do you think? Not horrible? Okay. What if I give you something like that? Y equals 3. Helps if my y stays there. We could think of that as y equals 0x plus 3, couldn't we? Of course, make that 0 over 1. So that means we would start at 3. How much would we rise? Nothing, and run 1. Y equals a number is just a flat line at that number on the y-axis. So what if I gave you x equals negative 2? That would be a vertical line at negative 2 on the x-axis. Now, we're not going to go into it in this course, but if you were to go on to college algebra or further study, one of the things that these are used for is solving problems. If you have two things that you need to meet at the same time, you might have an equation y equals 2/3 x plus 1, and you also have to satisfy the equation y equals 3/4 x. Oh, let's see here. This y equals 3/4 x. Let's see, what is that? So to graph this top one here, you would start at 1, you'd go up 2 over 3. Our line goes through those points. To graph this bottom one here, you would start at 0. Good. Think of that as plus 0. And we would go up 3 over 4. Our line goes through there. Well, at some point out here, these two lines are going to cross, aren't they? That'll be the point that makes both equations true. And that would be the solution to your situation. Now, I'm not going to get too far into that here. I don't want to give you an in-depth example because we're not going to do that for this course. But that is one of the powerful tools that these are used for, is finding when two conditions meet. Now, many of you that take economics, you'll talk about supply curves. As price goes up, the supplier is willing to supply more. And demand curves, as the price goes down, people are willing to buy less. Well, the point at which those cross is the ideal price. Okay, so our next thing, the last thing we want to look at tonight, is some data graphs. And data graphs are things you've probably already seen. These would be graphing stuff like, well, let's say we looked at favorite color. And by favorite color, we're limiting you a little bit. Let's say we're giving away keychains or whatever, and you get to pick between 3 colors: red, blue, and green. And let's say the frequency at which they're chosen. Let's say red had 17 people choose it. Blue had 14 people choose it, and green had 19 people choose it. This, by the way, is what's called a frequency table. It's used in statistics to organize information. Because let's face it, if I just recorded what somebody chose, oh, the first person chooses green, second person chooses blue, second person chooses blue, fourth person chooses green, fifth chooses red. I've got a list of those colors. Well, looking at that, it's really hard to get an idea of which ones chose most or not. So organizing it in a table like this helps us see that a lot better. Well, a way that would help us visualize it even quicker would be to put it in a graph. One of the graphs we might do is a bar graph, where we would put our colors down here, red, blue, and green, and up the side we have to do the frequency. Now, what's the largest number we have to go up to on the left side? We have to get up to at least 19. Notice I didn't mark off every space. I went up by 5s. Red is 17, so it has to go up that far. Blue is 14. Has to go up that far. Green is 19. Has to go up that far. Now you'll notice I made all these bars using brown ink. It would be really tempting to do red, blue, and green bars to represent the colors. The reason we try to avoid that is because some colors look bigger to the eye or they attract the eye more. For example, it's been proven red draws in the eye a lot more for most people. Red items put next to blue items or black items that are the same size, the red item tends to appear larger. Now notice I did something here, only half intentionally, but this green bar here ended up being wider than the others, didn't it? That makes it appear even bigger than it is, doesn't it? That extra width is deceiving. If I make it so it's pretty much the same width as the others, that difference isn't quite as profound, is it? So there are things you can do with these graphs that it can be very deceiving. A thing someone might do is, well, since nothing's smaller than 14, to make it look so you make it easier to see the difference between them, they might do this. Red, blue, and green. They might say, let's just start at 13. 14, 15, 16, 17, 18, 19. So red was 17. Blue was 14. Green was 19. Now this does help us see the difference between them really well, but if you're glancing at it quickly, you might look at the blue here and say, wow, the green is like 4 times, isn't it? But it's not. Up here we can see the green is larger than the blue, but not by a huge amount. So we have to be careful how we display those graphs. Normally they would put a big symbol right here, and in many cases they even might put a saw cut across the whole graph just to make it very, very clear and obvious that that axis does not start at 0. Now another type of graph that we could use this frequency table for is a circle or pie graph. Whether it's called a circle graph or a pie graph depends on the type of data you're representing. We're not going to get into the whole, numerical data versus categorical data argument. We're just going to look at how do we organize it and analyze it a little bit. This is what would be called categorical data. So it technically be called a pie graph for this. Pie graphs don't represent raw numbers. They represent parts of a whole. So a pie graph is usually represented with percents. So to find percents, I first have to find the total here. I add those up, and that's 50. So that means this would be 17 divided by 50, which is 0.34 or 34%. 14 divided by 50, which is 0.28 or 28%. 19 divided by 50, 0.38 or 38%. Now, years ago, we would have taken those percents. How many degrees are in a full circle again? 360. We would have found 34% of 360 to get how many degrees it was. We would have taken a protractor and measured out those degrees perfectly. But now we have computer programs. If we want a perfect little graph, we'll punch it in the computer. So if we're just sketching it out by hand, we can use benchmarks. We know that a quarter circle is what percent? 25%. A half circle is 50%. And of course, if I were to cut that quarter in half, that's like 12.5%, isn't it? So we can use those benchmarks. Up here, we have the 28, which is just a little bit bigger than a quarter. So let's just do it here and maybe like that. And that, of course, is the blue. We have red is 34, which is about a third of a circle, isn't it? Or I could look at it as 25 plus 12 and a half would be 37 and a half. It's a little smaller than that. So probably something like that. That's red. Then, of course, the last piece here is the green. We would almost never display them without putting something in there. 28%, 34%, 38%, so that you can see it clearly what those represent. If I were to ask you which color was most popular, it would probably be easiest to use which graph? The bar graph, right? You see which one looks tallest, right? Very quickly see the tallest bar. If I wanted to ask you what percent out of the whole amount was one of them, probably would use the circle graph, the pie graph. If I asked you which was chosen more, red or blue, probably look at the bar graph. The red bar is taller than the blue one. Red is more popular. If I asked you how many green ones were chosen, looking at this, it might be, is that 18, 19, or 20? It's a little fuzzy. If you want an exact number, you should refer to a table. Graphs are there to make a quick representation of the data. You can find the largest or the smallest easily, and you compare two of them easily. But if you want an exact number, you should go back to the table. Next type of graph I want to show you is for what's called time series data. What we did, what those other graphs are, the bar graph and the pie graph or circle graph, That's just looking at the data at one point in time. Let's say I wanted to track, we're going to come back every day and give away 50 keychains. And we want to keep track of how many green ones are taken each day. You know, we saw up here, we had several different possibilities, and we tracked all the possibilities. In a time series graph, we're only tracking one possibility over time. And to do that, we use a line graph. A line graph is always going to have the time across the bottom. So this is day 1, 2, 3, 4, 5. Let's just say they're going to do it each day for a week. So let's say 5, 10, 15, 20, 25. So on day 1, there was 19 of the green ones chosen. Day 2, let's say there were 21 of them chosen. Day 3, let's say it dropped to 14. Day 4, let's say it went back up to 19. And day 5, 18. So we connect our dots. Now, one mistake that a lot of people make is this. They connect that to 0. Does that represent anything? No, because at day 0, were there really 0 of them? No, we didn't do anything on day 0. So that really doesn't work. That doesn't show anything. What we can see really quickly here is when did the number of green ones take an increase? What increased between day 1 and 2 and between day 3 and 4? How do we know what increased? The line slopes up, positive slope. We can see very quickly where it decreases. Between day 2 and 3 and 4 and 5, the line slopes down, so it decreased. And of course, we can find 21 is the most taken on day 2. I feel like I have thrown enough at you for one night. So there is a new quiz due Friday at 11:59 p.m. There is a new homework for next Tuesday. Now, next week, Tuesday and Thursday are our last 2 lectures. So we're getting really close to the end. Make sure, remember we said, right now, out of the points possible, if you don't have at least 421 total points in Blackboard in the grade book, if you don't have that many right now, you're in danger. That number actually goes up to 520 by the end of the semester. So make sure you're checking. If you're not at least 421 points in Blackboard, contact me, and we'll see if we can figure out what we can do to help you raise your grade. Remember, there are always test corrections on the 3-unit tests. And also, if you have low quiz scores, and you want to redo some of those quizzes, let me know. But when you do that, send me an email. And please tell me the quiz numbers you need opened. Because if you just tell me an email and say, please reopen all my low quiz scores, it takes forever to dig through the grade book and find your low quiz scores. So please tell me the quiz numbers you want opened up. Okay, you guys have a great night. I'll be here till 5:20 if you want to work on stuff and ask questions. Otherwise, we'll see you on Tuesday.